Hello everyone. My name is Alex Davis and I am the co-chair of the newly formed IOP Space Group. And welcome to our first event. I created this group to fill the IOP's portfolio gap in representing the space domain and the careers of people working in this fast-growing sector. Future space group events will be advertised in due course. For example, we'll be running an exciting event on the 7th of October on the publication on the UK's National Space Strategy with the CEO of the UK Space Agency, Dr. Paul Bate, as well as other guest speakers. Can you move to the next slide, please? Thank you. The Space Group's mission statement is to promote, represent and connect interested people within the space domain. And today we are doing just that. Our speaker today will talk about one of the overlaps between space and quantum research. I would like to introduce Dr. Mark Bason, who is an experimental quantum physicist at RAL Space with over 10 years of experience in experimental quantum physics. His interests range from quantum sensing of magnetic fields for space weather to developing gravitational wave detectors using atom interferometry. He has industrial engagement experience through the UK Quantum Hub in sensors and timing and the Faraday Challenge. Previously, he was a Marie Curie Intra-European Fellow at the University of Aarhus, Denmark, and he is the secretary of the Quantum Optics, Quantum Information and Quantum Control QQQ group.
I'm glad you got that right. I get that wrong sometimes.
Googled it. Which is a special interest group dedicated to quantum science and technology. Mark's involvement in quantum technology stems from his undergraduate days in which he developed an interest on hands-on experimental physics and a desire to work with cool lasers. But first, the message to our audience members. Please remain on mute throughout the talk and type your questions in the Q&A box throughout. We will run through the Q&A in the final 15 minutes of the talk. But for now, I'll hand over to Mark.
Thanks very much, Alex. Thanks for the invitation as well. It's very kind of you to invite me, and really happy that the Space Group exists, obviously as being some interest in space, let's say. So I hope it's going to flourish, and I'm sure it will. Looking forward to the events as well, and joining not as a speaker, but as an absorber of information. So yeah, I'll move on to my slides. So I'm going to be talking about quantum instrumentation in space applications. So this is somewhat wider than my usual talk. It's hopefully aimed at a reasonable level where things aren't too simple and also not too complicated. But there's a lot of information in there. I don't have time to do everything justice, but I'll do as well as I can in the time that we have. And if you have any questions, then yeah, just add them in the chat, as Alex said. So my little symbols down here are meant to represent quantum. So we have an atom here and we have a satellite. So putting those things together and trying to do useful measurements and useful communications. So I thought I'd start just by saying where I am. So this is RAL Space. So it's the UK's National Lab for Space, as you might be able to guess. So we're part of STFC, so the Science and Technology Facilities Council, which itself sits within UKRI, and that sits in DSIT, and that sits in the government. So we all the way down, the money flows, and some of it gets to us. We try to do useful things with it. So RAL Space has been going for quite some time now. So we've launched over 200 instruments. We have a couple of sites, so in Harwell, which is where we are now in South Oxfordshire, also in Chilbolton. And we have excellence in a range of different fields, so from mission concepts to testing, engineering, satellite comms, and then yeah, fundamental science. And so a few of those things are bridged by the Quantum Sensors group. So that's the group I'm in. And we try to push and raise TRL of various types of quantum instrumentation. So it's a good place to work. Anybody looking to change career, I can recommend it. And so I'll just give a few examples of the types of missions that we're involved with. So James Webb Space Telescope. So one of the instruments there called MIRI, we had a large part in developing and testing that. Then there's a range of things coming up in the future. So SPECTRE is a quantum key distribution mission. Hopefully I'll get a bit of time to say something about that later. And then we're also looking at Vigil and Ariel and various other ESA and NASA missions on the horizon. And so our missions sort of cover all of these 4 different categories, or this is how we like to think about things. So all the way from Earth observations to telecoms and cybersecurity. And we've got a range of partners around the globe. Okay, that's my little advertising pitch done. So I'm actually part of the imaging systems group, and this comes from a camera electronics background. So there's some of the electronics for the cameras has been developed here. So this is an image from a NASA STO movie showing the sun in the extreme UV. So these are the prettiest pictures I'm going to have, or nicest movies in the whole presentation. So I thought I'd include them. So and it's also related to the space weather stuff I'll touch on later. So here you can see a solar flare being emitted. So these are the things that have impact on space weather, as I said before. So that's very nice. It's what we call classical technology, I suppose. So traditional imaging, taking pictures. And so the things we do in the quantum domain are sort of adjacent to this, complementary in many ways. So next slide. And so we do a range of different sensing. So from acceleration, rotation, magnetic fields, and clocks. So clocks you might not think of as a sensor, but we kind of think of it as a timing sensor. So measuring the rate at which time ticks. So the more accurately you can do that, the better. And so the best clocks in the world are now types of quantum clocks. So the last one is not really a sensor, but it's quantum communication. So this is the QKD, quantum key distribution application that I'll talk about later. And so we have sort of wide expertise in 3 of these. So acceleration, the magnetic field, and the quantum comms. And we're looking at developing rotation and clocks in the future, but it's not something I'll talk about in this talk. So these are called quantum instruments, I suppose, because they try to exploit quantum phenomena. So what does that mean? So typically people say superposition and entanglement, so exotic physics that's been developed in the last century. And also quantization is key to quantum communication. So all of our sensors and instrumentation try to make use of one of these different phenomena. So yeah, as a brief outline, I'll try to take everyone through a little bit of a starter course of quantum physics. So hopefully for some people, this will be a refresher. So it'll be a little bit about superposition. And then I'll talk about some of the processes that we use to make our sensors. So in particular, laser cooling, which is where you combine laser beams and atomic sources, and you take them down to very cold temperatures. So I won't say how cold, but we'll have more on that later. And then I'll look at a few of the applications of some of these things. So in particular, atmospheric measurements, magnetic fields, space weather, and then dark quantum communication. There's a lot to get through. Let's start at the basics. So quantum what now? I've labeled this slide. So it's just a very basic starting point. The periodic table is shown on the left. And we may remember that we have an electron, which is orbiting in a nucleus, which has neutrons and protons in. So we have the example of nitrogen there. And what we do in the quantum sensors group is actually mostly operate with the elements in either the first or the second column of the periodic table here. So these are like hydrogen-like atoms where you have one electron in the outer shell, and you can manipulate these with laser light. We do use strontium as well, which we'll talk about, which has 2 electrons. And that's more of a recent development in the field of quantum physics. It's not quite been studied for as long as, say, rubidium or cesium, but it does have some advantages, which I'll touch on later. So we have these electrons orbiting our nucleus. And then what quantum mechanics says, so from the Bohr model, is that you can get quantum jump. So I've tried to represent that here as a little glowing blob. existing in different discrete energy levels. So if we run the clock and we have the time, you can get an atom which is it's just sitting there doing nothing, minding its own business. Then you get a laser field which comes along, interacts with the atom, and then that promotes it up to a higher level. So then it can stay there for a certain amount of time before something called spontaneous emission occurs. So that's when it drops back down to the level it was in before, or another level, and then it emits a photon associated with that difference in energy. So this, again, may be familiar from undergraduate physics. The wavelengths or colors of these photons that are emitted are very well defined. So here, for example, we have I can't remember actually which example this is. It might be nitrogen. So we have emission at specific wavelengths. So here in the blue and the violet, and also in the red. So we operate with rubidium, where the main transition is around 780 nanometers, which is in the near infrared. But other ones like strontium are something like 461 nanometers. So when I say working with cool lasers was one of my motivations, that comes from sort of the range of different technology, as well as the aesthetic appeal of different colors of light. So okay, back to the atom picture. So we have an atom here which is sitting in a higher energy state. So as I said before, it can emit another photon and drop down in the form of spontaneous emission, but it can also be driven down. So this is something that Einstein developed equations for in, I think, the 1920s. And we like to treat atoms as simply as we can. So this is a 2-level atom. So here we've neglected the other states which may be around, and we say that the laser field that the atom is interacting with is only a very specific color. So we can ignore the very low probability that an atom will absorb either multiple photons of that laser, get excited to another state, or that it will absorb a single photon and go to a different state. So it can be driven down to this other state here. And so if you look over time, this is my cartoon in the top right, if you just took an average, you would see some atoms in the excited state and some in the ground state. And the total energy of the system, if you expose it to some laser field, might do something like this. So it might oscillate between 0, which is the ground or the lowest energy state, or 1, which is the excited state here. So quantum physicists usually label these using this bracket notation, which don't need to focus on too much, but G here stands for ground, E stands for excited. Tonight, this phenomenon here is called Rabi flopping, after a physicist called Rabi. And it occurs at a specific frequency, so maybe in the megahertz or something like that. And this here is meant to be depicted as an average description of the system. So we may have something like 10 to the 10 atoms in one of our experiments, so sometimes more, something on that rough order of magnitude. So one of the strange things about quantum physics is this idea of quantum superposition. So as before, I showed you this kind of average effect where the sort of average energy in the cloud could be oscillating. Here we have just we think of a single atom or a single ion, some particle confined in some space. And here we look at the probability now. So instead of just the total energy, we have the probability that it exists in different states. So at the start, it could be initialized in 0. So it could be starting down there. Then we can apply a laser field and we can look at this flop time. So this is just the time it takes to go from one state to the other. So then you can start with it in 0, as I said, and then after some time you can measure it and you can see that it's in the excited state here. So that's called the probability of 1. And the weird thing is in between. So if you apply this laser field for a certain time and then measure it, you either get 0 or you'll get 1. You don't get 0.5 of an atom in one state and 0.5 in another. So it will sort of collapse, it's called, into the different states. And if you repeat that many times, and you can build up a picture, some statistics, and that will say that you have roughly, say for this point here, 0.5 probability. So that's an equal probability of being in the excited state or the ground state. So if you drive this laser pulse at this Rabi flopping, and then you wait at this specific point, And until you measure the atom, you don't know whether it's in the excited state or the ground state. So this is something like the Schrodinger's cat picture, or phenomena that maybe we've heard about before. So we're going to use this, this principle of quantum superposition, and we're going to try to make a sensor out of it. So actually, this is not just theory picture. This is actually taken from an experiment between specific states in an ion of strontium, so strontium-88, specific isotope. And so this is one single ion held in a specific type of trap. We see this type of phenomena, and we're able to study it because we can cool these atoms down to low temperatures. So if you have an ion, normally they're excited. It's an excited state of matter in the sense that an electron's been stripped out of it, and they're very sensitive to electric and magnetic fields. So what people want to do is reduce down the temperature, which is reducing the velocity, and get it to stand still. So that's what I call asking atoms to politely stand still. And so we're going to get onto laser cooling now, which got the Nobel Prize in 1997. And basically, we're going to try to get atoms as cold as we can and as many as we can. And when I say cold, what does this actually mean? So in the movie that I showed at the start, we were looking at the sun, and so various different layers of the sun will have different temperatures. But if you look at the surface, it'll be something like 6 kilokelvin, 6,000 Kelvin. It's pretty hot. Room temperature about 300, all the way down to the cosmic microwave background, which is about 4 Kelvin, which people usually think of being particularly cold. But on the scale of laser cooling, this is actually quite warm. Even dilution fridges are a little bit hot for us. So we typically operate about 1 microkelvin, so very close to absolute zero. And then there are some experiments which make a form of matter known as a Bason, like condensate, which will get down below 1 microkelvin. And so the records now are getting lower and lower, so people have gone below 1 nanokelvin. So you can't get to absolute zero to zero Kelvin. That's not allowed by thermodynamics, but you can get arbitrarily close. So people are developing techniques to do that. Of course, if you make something very cold, but you immerse it in sort of a room temperature and pressure conditions, then you will see that other molecules and atoms will collide with it and heat it up again. So we need to do these experiments in a vacuum chamber. So like the one pictured down here, which is a lithium experiment. So there we make ultra high vacuum, which is something like 10 to the minus 11 millibar. So this is many orders of magnitude lower than the pressure on Earth. And we do that with a combination of technology such as ion pumps. So how does laser cooling work exactly? Well, it really hinges upon the transfer of momentum from a laser beam, so from a photon to an atom. So here we have an example of an atom flying to the right. And what we do is we set up our laser here so that we have photons firing out, which are opposing that motion. So they go in the opposite direction. So this atom here can absorb a photon and it can emit it. And what it does is it absorbs it from a specific direction, but it will emit it in a random direction. So if you repeat this over and over again, then what happens is you get a net transfer of momentum from the laser beam to the atom. And if you arrange that properly, and in this example here, you can get the atom to slow down. So if you think about this in another way, it's like having an elephant charging at you and you have a ping pong ball gun where you're firing lots of ping pong balls. So the momentum of each ping pong ball will be very low, but if you fire enough of them quickly enough, you can actually slow the elephant down. And the same is true here. So we try to choose intense laser beams with specific atoms. We try to scatter. So this process of emission is called scatter. Try to scatter as many of these photons as we can. Then we need to do this in multiple directions because once the atom is slowed down, what we don't want is the laser beam to keep pushing it so that it turns around. So we actually use multiple laser beams coming from multiple angles. And if we do this, then the Doppler effect, which is the same thing as an ambulance passing you in the streets where the sound changes frequency, we can do that and we can keep atoms in one place. So here's a little picture actually of a ball of atoms. This one has been cooled down to about 10 or 15 microkelvin. So it's about 10 to the 9 of those. They're trapped and then they're dropped. So here you can see it looping through. And this is the time that it's dropped for, so on the orders of milliseconds. So we can use this, the expansion of the cloud. So it's not obvious to tell from this movie, but the cloud will expand if it has a finite temperature. We can use it to measure the actual temperature and thus the efficiency of the laser cooling. Okay, so now we're going to look again at one of these sensors, so an accelerometer, something that measures acceleration. So for that, we're going to use the two concepts we just developed before. And so that's finds use, in particular, atom interferometry for things like geodesy and climate effects, so looking at mass movements. So hopefully now I can explain a little bit about how it works. So we start actually with a light field. So many of you may have looked at laser interferometers before. So here you have something like a laser beam, which is interacting with a beam splitter. The laser is then split into two directions, hits these mirrors, and then is recombined on another beam splitter. So if you then look at, you detect the light coming out of these two sides of this beam splitter. You can measure something like these fringes here. So this is an interference effect, similar to sort of waves adding up on the shore, once you've hit a harbor. And the interesting thing about this is it's very sensitive to changes in one of these paths. So if for example, this mirror moves by a small amount, and by small, we need to compare it to the wavelength of light, then that will result in a phase change. So these fringes will change, and the radii of one of them will move. And then we'll get a very sensitive measurement. So this is the basics of how interferometry works, and actually how some of the present gravitational wave detectors work. But if you think about it in a photon picture, so now let's say we have an individual photon, it hits the beam splitter, and it basically can go one way or the other. What happens is it goes into a superposition of these two states. So the photon travels both through this way and through that way. And then it's only in the measurements that we can actually recombine it, and we can read out the state of the photon. So the atom in atom interferometry is the same. So instead of light coming in here, imagine that you have an atom, and then you put it into superposition of these two states, like we showed before, and then you let those states spread out. So actually, we don't need to bounce them off mirrors. We can just let them fall under gravity, and then we recombine them with a laser pulse, actually, and we can read out which state the atom is in. So that's like detecting photons which have gone in one path or the other. So the interesting thing about using atoms is it allows us then to be sensitive to gravity. So this is an expression up here, simplified for the purposes of this, which shows that the phase shift, which is this delta phi, just the phase of one of these fringes, is proportional to the wave vector of the light that's kind of related to the frequency, and then little g. So that's the gravitational acceleration that the atoms experience. And then the longer you can leave the atoms to propagate, so this effectively the bigger the path that they travel, the larger the phase shift is. So this is proportional to t squared, so you get more and more advantage of letting them propagate freely. And then because this is sensitive to the acceleration, we can use this to measure gravity. You can also use it to measure acceleration. So how sensitive is this? Oh, this is, sorry, just a reminder that these things actually work in practice. So as you saw before in the previous slide, that was fringes of light. So these are now actually fringes of sodium atoms. So wave particle duality says that an atom can be a particle or wave. And here we detect what looks like wave-like behavior, and is wave-like behavior, but actually if you break it down, this is a single atom effect. So this will be composed of just individual atoms. So you can use this, as I said, to be sensitive to gravity. So some measurements done PTV in Germany a couple of years ago, which just shows how sensitive this can be. So we're errors down in the 20 nanometers per second squared range. So if you remember maybe in A-level physics or equivalent, one of the experiments I did was a pendulum, was a bit of mass on a string, trying to measure gravity by looking at the oscillation frequency. So there, I think you're lucky if you get close to 10 meters per second. And here we can measure down to 20 nanometers per second. So that then leads you to be very sensitive to different effects. So the Earth flattening is actually, you don't need to be that sensitive. So that's the geoid that we'll get onto later. But down at the sort of nanometers per second, you actually get sensitive to people near your apparatus. This is something that's so sensitive that it can detect if you're walking by it. And so we want to push the boundaries here. So 100 kilograms at a meter, just the gravitational effect of that is great. It's very impressive, but we want to push it down even to sort of smaller masses or further distances. Okay, so then back to the space aspect. How do you use these measurements of acceleration? So there's two ways that we've been looking at in the group here in RAS. This is my colleague Tristan Valenzuela, who's been leading this work. One is an atmospheric drag mission, and another one is for doing geodesy from space. So as I said before, we do this in vacuum chambers. A lot of work has gone into minimizing the size, weight, and power of these things. So this is reasonably large. This is about 50 centimeter scale here. And we want to combine these into sort of proof of principle missions to measure useful things, and then work towards measurements for fundamental physics. So quantum sensors are not the only way to measure some of these things. So for example, here I'll skip forward a slide. This is the classical version of a sensor that's already up there called Gocha. So this looked at measuring the Earth's geoid. So if you think about it, or if you measure the gravitational acceleration from space, then any changes in that acceleration are due to the distribution of the mass. So the density being higher in some places than others. This is an exaggerated picture, obviously, but you have the coast of Africa and then South America shown there. And we're sensitive down using this classical technique down to be able to measure changes in sea level on over about 100 by 100 kilometers squared, changes in sea level about 1 centimeter. That's pretty impressive already, but hopefully the idea is that using these quantum sensors, we can either improve that resolution of a centimeter down to, let's say, a few millimeters, or we can really look at sort of more narrow distributions, so improve the resolution, so maybe something like 10 kilometers by 10 kilometers. So that's one application. Another one is looking at atmospheric drag. So if you can measure acceleration, you can also measure deceleration. And this is interesting because things like the density of the thermosphere are not well observed and not understood. So this is an example here. Because the thermosphere depends upon solar activity, what you want to be able to do is measure at different times of the solar cycle and look at the effects at different heights and different altitudes. So there's a gap here which people are trying to address, which is above 300 kilometers, and then in periods of intense solar activity. So if you look at the drag, you can use that data to inform better models, and that in turn will give better orbit prediction. So if you want to, let's say, avoid collisions in low Earth orbit, you can get better models, and then you can predict better when these things will become a risk. So say large constellations of satellites will then have more information and be less likely to bang into very expensive things. Okay, I will move on to the next one. So that this shows, I guess, recent progress in terms of how we've been using 3D printing. So the idea here is that you don't want solid mass of metal for your vacuum chamber. You actually want to use 3D printing to sort of reduce the infill here to make things lighter. I have a little example here, a little plastic one, which I can talk about at the end. So this is a current project in the group here, done in collaboration with these two companies and University of Nottingham, and that's trying to develop a very compact version, which is probably about 30-40 centimeters in height. Okay, another application of atom interferometry is in fundamental physics. So this is now getting onto a ground-based instrument. And what it's trying to do is look at dark matter and gravitational waves. So first of all, dark matter. It's kind of embarrassing for physicists that we can't really explain what about 85% of the universe's mass actually is. So we're quite proud of our achievements so far, but we're hunting for an explanation for what dark matter is. So here we see some evidence of dark matter, which is this gravitational lensing effect around these galaxies. And then the second effect here is gravitational waves. So these have detected light-based interferometers already. This is my artist's impression of what gravitational waves look like. But just detecting them at specific frequencies is impressive, but what we want to do is to detect different frequency ranges of gravitational waves. So to do that, we're part of a collaboration called AON, which is Atom Interferometry Observatory and Network, so made up by these universities and us. And we want to do a similar thing to the rubidium type experiment I described before, but using strontium. So strontium has an advantage that you can drive interferometry just using one laser beam, whereas in rubidium you have to use two. So the idea is that you have a very long tube, and by long we mean 10 meters up to 1 kilometer. This thing is going to be vertical, and we have two clouds of cold atoms, so one about halfway up and one at the bottom, and we launch them inside the vacuum tube, and we let them sort of propagate under gravity. So if there's no difference in the gravity on these 2 points, then what will happen is that we will get sort of no change in the phase pattern that we saw before. But if we do have differential change in the gravitation, so that could be because of our gravitational waves interacting, and then what will happen is that we'll see a phase shift in one of the interferometers. So we're trying to make this as sensitive as possible by making this instrument as long as possible. So we benefit from this t-squared scaling. This is not the only experiment in the world trying to do things like this. So there's a collaboration that we have with a US experiment called MAGIS, which is trying to do it in a 100-meter detector. And there's also ones in China and in France, or MIGA and Zyga, which is trying to do it in similarly long baselines. And then the advantage of doing that would be that we would open up a new spectrum in the gravitational wave detection, which would sit somewhere between LIGO and LISA. So LISA is a space-based proposal for a light interferometer, and LIGO and Virgo are sort of ground-based interferometers that exist already. So this is quite a busy graph here. You don't need to understand all of it, but the more sensitive you are, the lower down in this plot we go. So this is the strain measurement. So measuring at different frequencies will allow you to be sensitive to different types of astronomical events. So colliding black holes, different size black holes. And if you can measure at certain frequencies, then what you can say is to your colleagues in LIGO that, okay, we're going to predict that in a certain period of time, you're going to see something at a specific location in the sky. So being able to hand over from one instrument to another is a bit like traditional astronomy, where you could measure the same event in different visible light or X-ray areas of the EM spectrum. Okay, and we have a lab that's developing that, one of 5 strontium labs across the UK. And here's a picture of some strontium glowing, fluorescing in a vacuum chamber. So another application is in magnetic fields. So here we'll just go through this rather quickly. And the advantage of using quantum sensors for magnetic fields is that you can take an atom and you can measure its properties, and then you can put that atom somewhere, let's say on Jupiter, and its properties will remain the same. So whereas in classical sensors, you may have some systematic effects, the idea is that using quantum sensors, you should dramatically reduce those systematic effects. So have something which is much more accurate. And that's important because the types of missions that we want to use these sensors on are over very long time scales. So we don't want to be doing things like recalibration if we can avoid it. The second advantage is that measurements, so this is a measurement here of an atom, will give something that's fundamentally linked to an SI unit here. And so we do this by measuring precession. So precession is something like a spinning top you may be aware of, and the laser beam. So the laser will both prepare this precession and it will read it out over time. And so the result is you get something which is both accurate, so the readings are very close together, and precise. It's not the first magnetometer in orbit, of course. There's been ones dating back all the way to the 50s, so to Sputnik. But the most successful of these is actually called Swarm. So it was launched in 2013, and that's been taking measurements ever since. And the accuracy with which it does that is something like 0.5 nanotesla. And that's very good because you should compare that to the Earth's field, which is about 50 microtesla. So these are useful both for building up models of the magnetic field of the Earth. So this is very much dipolar, so it's like you have a bar magnet in the Earth. But the higher orders of magnetic fields will tell you something about various different goings on in the mantle or in the crust. So that's one advantage. And then looking at space weather is the second one. So the impact of the sun on the Earth will depend upon the magnetic field of the Earth. So this is an example here from ESA. You'll have some coronal mass ejection, so that could give some radiation dose. That could upset cause some damage to satellites. So it's something we're very conscious of here. And that can also induce issues in the Earth. So you can get currents generated in the crust here. And that current can feed into the power system, so the power lines here on Earth, and that can upset operations, and it can actually fry electrical substations. So we want to be able to measure this, predict this, improve our models, both of solar radiation and the impacts. And so we have to measure the magnetospheric field, which is around 20 to 30 nanoteslas. So we need an instrument that can do that. So one of the ways of doing this is on the Earth. So we have a collaboration with the British Geological Survey and the University of Strathclyde. So this is a project ongoing at the moment where we want to place ground stations. So these are types of observatories. And we can build up then a better picture of what the magnetic field will be across the UK. And then we'll be able to make more localized predictions of what the effects on the ground will be. So we have with various steps along the way in that. So we're looking at using these rubidium or cesium cells here, which are very compact, and then developing electronics to be able to read them out. Okay, so then I'll quickly go through the last one, which is the quantum communications, which I promised at the start, so we want to try and go through. And so this quantum communications came about partly because of the growth of another area of quantum technology, which is called quantum computing. So quantum computing threatens traditional algorithms, which rely upon the factorization of large numbers. So for example, if you use a credit card, cryptographic methods will rely upon it being easy to multiply two large prime numbers together, but make it very difficult to do the opposite operation, which is to do division. The quantum computers promise to do this much more quickly than traditional computers. So we want to try and find a better way, a more secure way to communicate. And so the current hot topic now at the moment is quantum communication. So this is actually already operational. So the Chinese had this mission in 2016. And so there, what they did is exchange these cryptographic keys. So a key is a crucial piece of information that you need to be able to decrypt messages. And it uses single photons, so it's very individual quanta of light, and it's in quantum superposition states. So very briefly, I'll try to explain the basics of how this works. So I'm not going to go through the full mathematics of it, but I'll try to give an indication of what effects this relies upon. So we have individual photons. So these are what are called quanta. So these are little packets of light. And just like in traditional optics, your electromagnetic field will be oscillating in a specific direction. So what you can do is use these polarizing filters. So this one would be, say, vertical polarized, or you could rotate. You start with one particular polarization, have another filter, and you could then let through light of a specific polarization. If you have a filter which is going in the opposite direction to the polarization, then you will get light attenuated. And so this is Mallister's law, which maybe you're familiar with. So what we're going to use in this is a specific basis. So horizontal measurement or a vertical measurement, and then a diagonal one. So these are kind of like a key, maybe not a key is the best way to say it. These are like a guide to which measurements you have to take. So that's how I'd explain the basics. Then photons are, when they're detected, are destroyed, and then quantum physics says they can't be cloned. So if you have a vertical one, if you measure it, you destroy it, and therefore you can't copy its properties onto another photon. So there's something called the BB84 protocol, which is the classical, which is the prime example that people give as a quantum cryptographic method. And this relies upon this relies upon a special protocol whereby you have an Alice who is preparing the message and Bob who wants to receive it. So they communicate over both a quantum channel, so sending single photons, and also this classical one. So they can send the information over here, but they can send the key through the quantum channel. What happens is that Alice will choose specific bases of polarization of light. So either horizontal, vertical, or these different diagonal ones. And she won't tell Bob what they are to start with, and Bob will also choose a random basis here. So they both select random bases. They fire a load of single photons. So then Bob will measure these photons and he'll keep what he measures as a secret. And the next stage is that they share what bases they've used. And then they will look at when they have matching bases. So this means, say, Alice has chosen horizontal for her, let's say, 50th photon, and Bob will say whether he's used horizontal or vertical measurement for that 50th photon. So where they've matched here, then they will keep that data. Where they haven't matched, they will throw it away. So what happens is that then they will take a small fraction of these measurements, and then we'll compare the results and look for agreement. So if there's been an eavesdropper, which is commonly called Eve, then what happens is that this measurement here will get disrupted. So the statistics will change. So I won't go through the full maths of this, but the key parts of it are that the bases that are used are declared after the photons have been sent. So if Eve measures a photon, she collects it, she measures it, she doesn't know what basis to transmit it in. And that's because she's only detecting a single photon, and there's a 50% probability that she's measuring in the right basis. So she has to choose the right basis and emit it again. And if she does that, then there's actually a quarter probability that she introduces an error. So if she does that, what will happen is that Bob and Alice will compare their results and they'll say, oh, we got something slightly different. There's something going on here. And so if the errors are large enough, they will say, okay, someone has been interfering on a line. Let's scrap this key and let's then generate another one. And so if you want a more hands-on demo of how that works, I really recommend this resource from St. Andrews. So here you can work through the mathematics and you can change the filters, and it's a good resource to see how things work. So RAL Space are developing two projects using CubeSats along these lines called Spectre and Spock. And they're slightly different in terms of how their key distribution works. So don't have time to go into that there, but they're planned to be launched next year. So that's all very exciting for us here. And then at that point, I guess I should probably wrap up and say thank you very much to the people involved. So these are physicists and electronics engineers and mechanical engineers who've been working with us. And then thanks to Alex for the invitation again, and hope you've got some questions.
Thanks, Mark. That was brilliant. A really nice overview, a really nice summary of the work that you're doing. We do have a couple of questions that are coming up in the Q&A. We've got an anonymous attendee who's looking to understand a little bit more about quantum phenomena, and they say that the photon emitted after the electron has its energy dropped back to its original energy level, does it contain the same amount of energy as the photon needed to excite that electron? Is that process therefore 100% efficient?
Okay, yes, I have some. So yeah, it's a good question. So if the atom was completely still, then it would be the same amount of energy. But actually, the laser cooling will rely upon this being a slight difference in energy. So if you think about having your ball of atoms, so in the laser cooling example, what you actually want to do is extract energy from those atoms. So you want to cool them down, which means reducing their energy. So the photon in that case will carry a little bit more energy than it did coming out to take that energy away. And then the second part, assume that a photon electron efficiency interaction has an efficiency of 100%. No, that's why you need to use lots of photons effectively, because depending on which atom and which transition in the atom you're working with, it can be quite a low efficiency. So we call that a cross section in a similar way to nuclear physics. So yeah, some of those can be very, very narrow. So it's very unlikely that a photon is absorbed. So particularly in strontium, you have very low cross sections.
Okay, and we have one more question that's come in from John Broom, who is the co-chair, or the other co-chair of the space group. So thank you for tuning in, John. He says it's a very interesting technology and a great talk. Thank you. Can we use atom interferometry to analyze ocean internal wave dynamics? For example, dH by dt, where H is the thermocline. Examples are long Rossby wave propagation along the equatorial waveguide and the subtropics.
That's a great question. So first of all, atom interferometers are sensitive to the tides. So from the very basic point of view, you can see the tides from Birmingham if you have an atom interferometer. So the actual wave dynamics, I guess, it depends where your sensor is, whether we're talking about space or on the ground. So I think for the ground ones, one of the places we want to put AON is in North Yorkshire, so in a place called Bulby Mine. So they have a very long mine shaft there, and we want the vertical one there. And so there we're expecting to be sensitive, or we will be sensitive if it's placed there, to dynamics. And so what range we're sensitive to the dynamics depends upon how sensitive our detector is. So I think it will depend upon how sensitive we can get in the end, and the propagation around the equatorial waveguide. I think we're probably looking at some space-based experiment to do that. But it's a good question. Yeah,
okay.
Possibly.
Good. And I have a question as well, actually. I was wondering why it is that you would want to make your 3D printed chamber out of this scaled down, sort of streamlined model. Maybe you could talk a little bit about that.
So this is just that, I don't know if maybe I can stop my screen sharing so people can see a bit better. So this is one of the plastic models of a titanium vacuum chamber that my colleagues have been developing. So it has various different compartments, so for various stages of laser cooling. And so people want to make it out of titanium because that's non-magnetic. So magnetic fields will interact with the atoms and give systematic effects. And the 3D printing has the advantage that you don't have a solid chunk of material to machine into, so you can actually reduce the mass by having special areas of support. So depending on where you're expecting the stress and strain to be, so it reduces the bulk.
And is that for launch, for flight? So that sort of, when it's made of titanium, could actually be flying in space.
Yep, that's what we hope.
That's the goal.
That's the goal. Yeah.
Fantastic. Okay. That's the end of the questions. Unless anybody has anything else they would like to ask, you can put that in the Q&A now. But otherwise, big thank you to Dr. Mark Bason for explaining his work, his research that he's there doing, and reminder to everybody that the space group is newly formed, and we're going to be putting our events up on the events portal throughout the year. And a reminder that we have our 7th of October event on the National Space Strategy, which will be a hybrid style event. So if you want to attend in person, or if you would rather attend as an online attendee, that will be run hybrid style. So please keep your eyes peeled on the IOP events portal for that. Great, so that's the end of the webinar. Thank you everybody for tuning in, and look forward to seeing you at the next thing.
Thanks.